Welcome back. We are continuing our journey down LeetCode's most common interview problems list. Today I have two tree questions. The first is lowest common ancestor of a binary tree. Given a binary tree, find the lowest common ancestor of two given nodes in the tree. According to the definition of lowest common ancestor, it is defined between two nodes P and Q as the lowest node P that has both P and Q as descendants. We want to find the lowest common ancestor in a binary tree, not in a binary search tree. These two are different. I made this mistake first time around. P and P is 5, Q is 1. So the node that has both P and Q as children, as descendants. Lowest node in T. T means tree, right? Yeah. Second example. 5, 4. So answer is 5, because a node can be a descendant of itself according to LCA definition. Okay, so if we can't find it, then we just return the we can just return 5 or 4. Okay. Since the precaution depth first search. Now, typically what we would do in depth first search is, in most tree questions, if we come across a null root, we return from there. We end our depth first search at that point, because there is because we have found the last level in a tree. But here we want to break our search only when the when the root is either P or root is Q, and we want to return the root itself. P is 5, Q is 1. If P is 0 and Q is 8, then this 1 is the root. If P is 6 and first node is 6, second node is 4, then their common ancestor, lowest common ancestor, would be 5, because 5's immediate child is 6, and 4 is its descendant. Well, we can also say 3 because 3 is the lowest. For 5, okay. So just what we do in a normal, the typical tree question, we check the lowest common ancestor. This will give us some left, some tree, we don't know what it will give us. Check right side. Right. Check the right side. So we don't know what left and right is going to be. If left is equal to B, or left is equal to Q, and right is equal to Q, or left is equal to Q, and right is equal to P, we have found our answer. Return the root. Well, if both of them are null, we also need to check the null condition. Well, if left is equal to null and right is equal to null, return root. What does that mean? What does it mean if both well, the result can never be it can never be a null root. The result can never be null, right? If there is if we can't find the and our ancestor, then we can simply return the P or Q. So if both becomes null, then that means we weren't able to find any ancestor. If either of them is null, we can return the non-null value. If left is null and right is not null, then return right. Else if right is null, and left is not null, then just return what's not null. It's very lengthy. Let's say return left is not null, left. Alright. Oh no, I mean P. If both of them are null, we simply return P. If either of them is null, let's see. Okay, we are starting at the root. We check left first. Root is equal to P, so we return at this level. Now we are checking now 3 is right. Right side, we're checking the right side. No, there is no match for. No match Q, no match for Q. So this side will return null. So basically return the non-null element. We are here. This is an easy case. So return root. Root is null. Return null. Let's check left. That's true. When would be applied when give. Common ancestor. Oh, P and Q. P, Q, P, Q. Oops. Some expected -1, but it returned 0. Expected minus 0, 3 p. Okay, there is a we started the root -1, left side 0, left side -2, and this is the last node, and we found the queue here. So we should have returned. No, this is wrong. Okay, so at this level, it's a left return this node. There is no right, so this side, so it returned null. Left is 8, it null on the other side. Now it will check if either of the node, and both of them are not null, and both of them don't have right values. 8, we found 8. Here's the 3. It's returning. I don't think we need null. So if left is not null, which it is not, return. But how? Okay, so the control comes at this root. Its left result is 8, and we check its right. It's not the node we want, so it return 0. Return null from here. It will. So 0's left is 8, and again we'll get 8 here. From this entire tree we got 8 as an answer. Now it will check the right side. Well, we have found the 3 2 A2 3. If root is equal to P, well, we have found both nodes. What's the problem? If is P and right is Q, or left is Q and right is P. P. Our left is Q and right is P. Minus 3 should be the result. No, minus 3 should not be the result. Minus 1 should not be the result. No, minus 1 should be the result. B for some reason returning 0. It's as if we are checking only this level till this level. Why is 0 being returned? Println the root's value. Root's value. See, both nodes. Value. Zero. Why is that? Let's check what's happening. Left dot value right dot value. After this, can P and Q themselves be null? Null order exception? Boy. Well, if we don't need to check this condition at all. Let's rule out all the invalid cases first. And if none of the condition hits, then we know the root is the answer. Just remove this. If only left is null, if left is not null and right is null, return right. If right is not null and only left is null, return left, return right. Well, if Okay, second case. Expected 5, but we are getting 3. Expected 5, but we are getting 3. So 3. Expected the root, but we are expected the root. No, expected the child, the p, but we're getting the root. In the second case, we're starting at 5. Once we found 5 on the right side, we don't check further down. We return from here. So now 3 is immediate. 3, we know 3 is immediate left child is one of p or q. Now we check the entire right subtree, and it is null. So according to this, according to that, 5 p is left is not null, then it should return left. That is 5. If right is not null, expected 3. We found the 5. We haven't found the 4. We haven't checked the 5's nodes below 5. So it should go to this case when left is not null. No, when left is not null and right is null, then we return left. That means we return p, but somehow the output is 3. Root is p, root is q. PQ output 3. If the output is 3, then that means it's returning the root. Obvious, pretty obvious. Now why would it return? It would only return so it would only do so when right's value is not null. Five right's value is 5 and then it ones. What? What? I think this OR block is causing me problem. What if we found a 5 here, right? What if there was another 5 somewhere here? So we could find the same children twice and it would say it's a valid thing. So yeah, this is where the problem is. How do I prevent this? Can there be duplicates? There be duplicate API exists in all nodes. Okay, all are unique. Don't need to worry about that. P and Q will always exist in the tree. Okay, so no problem here. No problem here. If root is equal to P, then return P. If root is equal to Q, return Q. So we're getting 5 as a right tree, as right's value 5. Why? Okay, left value 5 5. Great. If root is equal to P, if root is equal to Q, return Q. We have a left and a right. How can we get similar values for both left and right? Okay, so we come here, come here. So null, it is equal to P So we return B, and then we're back at 3. Then we simply go and check the right side. How did this duplication happen? Okay, 35 minutes. It's a good time to look at the right code. If neither of them is null, if neither of them is null, we don't need this condition then. Okay. If left is not null and right is not null, then we have found we have found both P and Q. Right, if is not null, return right, or we just left. P and Q, right? I don't know what's happening. Okay, all right. If we haven't found anything, we simply return a root. Okay, that was the main thing. Okay. Still have problems. We are almost there. We never return P and Q. Why? I thought I knew this question. God, this is awful. We never return P or Q themselves. We always return their root. Why is that? The root. We have found 5. We come back to 3, but we simply return 3. Okay. So 3's left is now 3. 3's right is also 3 because uh, null, because of null. So when, and this condition, when neither of them is null, we simply return the root. Okay. What is the space, time and space complexity? Uh, it's linear. It's linear time. It's a simple depth first search. We know that P and Q will always exist in the tree, but if they happen to be the leaf nodes on the very right and very left side, on the very on the leaf node right in the left and right subtree, then we would have to uh, iterate the entire tree. So that's worst case scenario. It's it's an checking each node exactly once. Space complexity is we're not using any additional space other than recursion call stack, so it's also an okay. I just spent good 5 minutes trying to figure out why it should work. Uh, it makes sense, but I don't know why. The fact that we know that the nodes would be there in the node, would be there in the tree, but that doesn't guarantee that we would find them. For example, in this case, or we can add when it's not a simple solution like this, we can hope to find only one of the nodes because of the condition that they both have to be the descendants of a single node. Okay, we'll definitely come back to this problem in a couple of days. Construct binary tree from pre-order and post-order traversal. Given two integer arrays, pre-order and post-order, where pre-order is the pre-order. Okay. Pre-order. In pre-order, we first print the value and then traverse the tree. So we print 1, then go to left side, print 2, then check the right, then go to left 4, come back 5, come back here 3, check 6, 7. Post order, we after traversing the tree, so we've traversed this entire tree, we found our leaf, so 4, come back 5, no 4, check the right side 5, 2, 6, 7, come back 3 and 1. Okay, so in pre-order node will in post-order root node will always be at the end, and pre-order node will always root node will always be at the, will always 1, 2, 3 will always be at the start. Let's see. We have to construct a binary tree from this array, from these arrays. Mm, mm, from here we can figure out our root, but we can't figure out the height of its uh, left or right subtree. It's guaranteed that P and R. Okay, hash map binary tree. Okay. Can we construct the tree just from this information pre-order? Well, we know the first element is root. The first one is root. Then we go build the left side 2. But no. 5, 2. Mm, First number will always be the root. Second number. Well, through this we can find out. We have to find the. We have to find this 2 in the post order and check the left side. Count the element. Then we know how many children 2 has, and on the left, no, totally wrong. Okay, 2's left and right child. Okay, 4 and 5. Um, I don't know. Not sure. How do I begin this? Well, we know that root is going to be pre-orders 0. Now something has to happen between roots left. Roots left. Private void construct tree. What information will we be needing in order to construct a tree? Tree node. Well, first of all, we need to know we need some sort of index. Uh, well, if you're talking about index, there's gonna be problems. We need to locate we need to locate the root in the post order. Well, for that to work, we'll have to iterate through the array. Or how do I keep a hash map? I need a hash map first of all of the, of the indexes. I can map each node in the pre-order to its corresponding node in the post order. So for example, here one is at 0th index and this one is at last index. We can simply ignore the element at first and last index. Here 2 is at first index and 2 is at here 0 1 2 index 4 4. Okay, so how can we use this information? Let's see. If you well, we can simply ignore the 2. It's at 2 is at in post or it's at second index, then 4 is at first position, 0th position, then 5 is at first position, then 3 is at 0 1 2 3 4 5 fifth position, then 6 0 1 2 3 4, then 7 5, no, 0 1 2 3 4, this is at 4, 0 1 2 3, this is at 3. Does this help me? No. Or I can well, this is really hard. Okay. Pre-order. Post-order. Index +1. This is where we will have problems. But I'm just, this is still too vague in my head. One, two, 4. Can we just take a very simple example? Let's say 1 2. SL3 is only 1 2 3. So 2 and 3. This is the pre-order. Post order is 1. 2, 3, 1. Now how can we construct a simple tree from this information? That what we would like is this tells us about roots information, and its next node, next element. This, well, we can check this from here. There is nothing on the left side of this, so we know that this is the leaf node. Okay, and we want to ignore the, okay, let's ignore the second. Oh, it's the same thing. So yeah, some sort of index. Well, we want to check. Here's what I'm thinking. Hash map integer map new map. Well, if map dot get pre-order index. Now this should get us the index of this element in the post order array. Post order. Okay, so we've got that. Now what to do? Can we do something like, if it's tree node agency list, 1, one's right child is 2. So here is that 2. Now we don't know 4. Okay. If you just iterate this array from this information, I need to find 2, 3, 2, 4, and 5, 3, 6, and 7. 4, 5, 6, 7. So, what does that mean? What does that tell me? That when I'm at 2, I need to find what's on the left. Just have to add those elements. Then when I'm at 4, I'll have to find 4. There is nothing left on the. There's nothing left to the 4. So just keep the array empty. Then I have 5. Now this is where the problem is. There is a 4 to the left of 5. Six, 5. Well, we have already created 5. Something like if map dot pre-order index into null. Then we create a node, tree node. Root new tree node pre-order index. No. Well, building the agent adjacency list, it's also a good idea. Just take care of a couple of edge cases. What if we start from post order array? We create 4. No. 4, and then we create another node. 5. Mm, we can use pre-order to know what's the next route going to be, but for the children we can take help from post order, but it doesn't help much. For 2 for 2 to 2, well, we know 2's left children and 2's right children. So we can kind of assume from this. This is very rough work. Um, uh, post order. Well, index going to be 2, index 0 or 1, 1, index post order root dot right construct tree index -1 post order array just have to check if index is within bounds. If index is smaller than 0 or index is greater than array's length, we return null. else we just create a tree node and who and you construct left subtree and then we return this. Okay, now so once I get access to, well, this is our main road. Once I get new tree node pre-order 0. This the end, and I want to pass in construct tree index, some kind of index. Now array one left and right. It's passing in. I think I kind of figured out something. So this is a very simple tree. It'll have one, and we kind of always know that the root in the post order is at the end, so we can use that index at the end. end. So this is at the end. Construct tree. It's going to be last index. Post order size, not length. Not length -1 and array 3. I think I'll have to give up. Nah, I'm so behind. No, I can't solve this. Let's study now. Root, subtree, right tree. The first element in is always the root. The last element is always the root. The second element is usually the root of left subtree. Using it, divide arrays. Cannot pre-index to track the current root of the. Use a heap hash map to store the index of each. Post or I is I. Start and if start is greater than end or check root pre-order pre-index plus plus. So incrementing the index immediately after accessing the post pre-order. If start is equal to end, what did get? Oh, this seems very complicated. Index of pre-order and post-order array. Okay, that's it. That's all right. I I got the basic idea how this needs to be done, but I actually need to practice and draw out recursion tree to like actually understand what's going on here. Okay, so yeah, this was a tough question, and I couldn't do it. But that's fine. That's why I'm doing this thing. I'm practicing. Okay, bye bye. I'll see myself tomorrow.